Okay, so the last thing we're going to do here is take this together. We found if it was liquid or liquid vapor mixture. We found some properties, and now we're going to use that to work on a first law problem. Now I'm going to tell you, you're going to need much more practice than what you have right now in just this lecture. So the homework's going to help you out. We're going to have two in-person sessions where I'm going to just be setting states and practicing with setting states, where I'm going to be putting something on the board, kind of letting you out there work on it. It's something that you need some practice on, and we will do that practice. I posted a couple documents on Canvas for you. There's the chapter to read. I really encourage you to take advantage of all these resources. Okay, so let's look at this problem. And this was the last page of my PowerPoint for the previous lecture. It says a piston cylinder assembly contains 2 kilograms of water at 100 degrees Celsius and 1 bar. So as you're writing here, I'm going to be, you can't see my screen here, but I'm going to write something here. I'm going to write state 1, and I'm going to write state 2. Okay, I'll just show you so you can see. I'm writing state 1 and state 2. Okay, and then I'm going to start writing down what it says. It says it has 2 kilograms. So we have 2 kilograms, and it's water, so it's H2O. And it says it starts out, temperature 1 is equal to 100 degrees Celsius, and our pressure 1 is equal to 1 bar. The water is compressed to a saturated vapor state, so state 2 is a saturated vapor, and the pressure here is 2.5 bars. During compression, there is heat transfer of energy from the water to its surroundings, having a magnitude of 250 kilojoules. So Q is equal to 250 kilojoules. Now, I have to look there. It said it in words. There's heat transfer from the water to its surroundings. I'm going to make water the system, so that means this is going to be negative 250 because it's leaving the system. It says neglecting changes of kinetic and potential energy, determine the work in kilojoules for the property. Okay, so look, they're kind of listing everything like I wanted to. Here they're showing states here. They're giving state 2 here. They're doing this. They're drawing out the system. This is what I'm going to do on my homework sheet. And here is going to be my TV diagram. Let's do that for ourselves so we can see what it looks like. So we have this. We have our piston cylinder. We have our water in here, and this is going to be our system. 2 kilograms of H2O. Okay, we have leaving the system 250 kilojoules of heat. Okay, now we want to figure out what the work is. Okay, what the work is. And you might say, oh, work, I know work, Dr. Wankler, work is equal to the integral of PdV. All right, well, that's one way to find it. That is one way to find it, absolutely. But what we're going to do here is do it another way. We're going to use the first law and see if we can do it with the first law. We can say delta KE plus delta PE plus delta U is equal to Q minus W. And we know that the kinetic energy is negligible. We know the potential energy is negligible. And we know what the heat transfer is. So if we can find out what delta U is, we can solve indirectly for work. Okay? And that's exactly what we're going to do here, because we have 2 things for each state to set the state. Okay? Now, I don't want to use integral PdV because I have pressures are different, and I'd have to find out what my specific volumes are, and I have to figure out if it's a polytropic process, and all these kind of things I have to do. It's actually easier here to use use this equation. Okay, so if I go down here, I can say I have 2 things here. I can set the state. I can figure out what my internal energy is at 1. So let's go ahead and draw our TV diagram. And we are drawing a line of 1 bar. Okay, so let's go to our document camera. And we're going to go to 1 bar. And I find that they saturate at 1 bar at 99 degrees Celsius. This is going to be 99 degrees Celsius. Okay, 99.63. Okay, I am barely above that at 100, but I am above that, so this is my state 1. I am a vapor at state 1. Okay, I'm a vapor at state 1. State 2, it says I'm at 2.5 bars. And the second bit of information it gives me is not a number. It doesn't have to be a number. It's telling me it's a saturated vapor. And so I know where I am. I am right here. This is my state 2. Okay, so my process from state 1 to state 2 looks like this. It goes from state 1 to state 2. So they don't always have to give you a number to tell you about the state. You can find that out just by the information, the pieces of information. You need 2 pieces of information to set the state. Okay, now I can go look in my tables and find out what U1 is, internal energy 1, specific internal energy 1 is, and then what specific internal energy 2 is. Okay, so at saturated vapor at 2.5, let's do that first. Saturated vapor at 2.5. Here's 2.5. And look, now we're going to go into our internal energy charts, and look, there's a saturated vapor. So for 2.5, here's where your saturated vapor is. So it might be nice to have a straight edge as you're looking at things here. And this is going to be 2537.2 kilojoules per kilogram. Okay. 2537.2 kilojoules per kilogram. Okay, now for our other value, we need to go to our superheated vapor tables, and we're going to go look at 1 bar. Okay, 1 bar. Here it is, and 100 degrees Celsius. There we are, 1 bar and 100 degrees Celsius. And we're going to look in our second column, which is our internal energy, and we're going to get that's equal to 2506.7 kilojoules per kilogram. Okay, we've set the state. We could find the specific volume if we wanted to, but that's not how we're approaching it here. So now I've looked up in the tables, I've looked up this value here, I've looked up this value here, and now I can solve this problem. Because the problem is going to be that the mass, that's what I want to do. I change my color here. The mass times the specific internal energy 2 minus the specific internal energy 1 is equal to Q minus W. And so I knew here that I had 2 kilograms. My U2 value is 2537.2 minus 2506.7 kilojoules per kilogram is equal to minus 250 kilojoules minus my work. Okay, and so I'm going to solve this, and it's going to say that, and let me just pull out my calculator to do this with you. Oh, you know what? Let's make this the quiz question. Answer, what is the work? What is the work? And give it with the sign. Is it positive or is this negative? Now, the problem statement has a very big hint there. Let me just go back to the problem statement as well. The problem statement says during compression. Okay, you should know what the sign is, but your answer should have the sign that verifies that. Okay, that's what I have for you today. Like I said, we're going to practice this again and again. If today's lecture seemed like it was going fast or you're pausing things, I got you. I understand. We are going to work in person to kind of just practice this over and over and over and over. If you're not feeling comfortable, ask me, ask my 2 TAs. Let's figure this out, okay? Because you're going to be needing to do this on every problem from now until the end of the semester. All right, I will talk to you later. Enjoy whatever day it is that you're reading this. Enjoy the day. All right, we'll see you later.